Reinforcement learning is demonstrated in OpenNERO using the maze environment. We have two different Q-learning agents, coarse and fine, available. In the coarse version, the environment is divided into an 8 by 8 array of states, which are indicated by yellow markers. Around each yellow marker, there are 4 blue markers, which correspond to the 4 Q values for the 4 possible actions that Steve can take in each state. As Steve is exploring the environment, those Q values are being updated, and the visual is also being updated to reflect the relative Q values for each state. For example, if Steve tries to run into a wall, which it just did, then it receives an immediate reward of -1, and that makes the Q value for that action go down, and then the other actions start looking better for that state. Likewise, if Steve manages to get to the end goal, which is indicated by the red cube, it will receive a very high positive reward of +100, and then at that point, the Q values will start propagating back to the states that led Steve to that end goal, and then the learning process is progressing. So our job here is to help Steve get to that end goal as soon as possible because it starts with an value estimate of 0 for all Q actions, and until it gets to that end goal for the first time, it doesn't really know the proper Q values for any of the states. So to do that, we have a couple of options available to us in the control UI. For one, there's the speed up slider, which just allows us to speed up the visual and makes Steve go through the maze faster and faster. Another option that's available is the explore exploit slider. If I increase that to, let's say, 60, then what I'm telling Steve to do is to take random exploratory actions 60% of the time. And what that allows it to do is to explore the maze faster and faster during the earlier phases of the learning process. And that will make it more likely that Steve will get to that end goal by some random action, and then we'll have a chance to see what state can get it to the end goal. And that has actually happened here. These green states, what that means is that Steve has managed to see a path from those states to the end goal, and those states have a positive value estimate above 0. So once that happens and more states turn green, we can gradually lower this explore exploit slider so that Steve just follows the optimal actions from the initial source state to the end goal. So still Steve is doing exploration, and that is normal. It's part of the learning process. And as you can see, more and more states are turning green. And then at some point, the source will turn green, meaning that Steve knows how to get to the end goal from the source. It has happened here, so we can decrease the speed up and see that. So I'm also decreasing the explore exploit slider so that Steve takes optimal actions from each state and doesn't try to explore anymore. So as you can see, Steve knows the proper actions that can take it to the end goal as fast as possible, and this constitutes a shortest path from the source to the end goal. Another option that's available to us is this starting offset slider. Let me reset the learning. With the starting offset value at 0, Steve is starting at the source all the time. But if I increase that to, let's say, 11, which means I want Steve to start at a state that has Manhattan distance of 11 from the source, which would be closer to the end goal. Let's actually make that a little larger. So if I do that, I'm telling Steve that I want it to start very close to the end goal. And that might be useful because reinforcement learning really learns from the trailing ends of the episodes. And as soon as it reaches the end goal, it's more likely that it's doing some useful experimentation and the values that it's learning are actually proper Q values. So that's another option that's available to us. Unfortunately for us, in this case, Steve started in a kind of cul-de-sac area in the maze, so it's not really easy for it to get to the end goal. Another Q-learning agent that's available is the fine-grained Q-learning. And in this case, let me reset this to 0 as well. In this case, the environment is divided into a 64 by 64 array, which is about 4,000 different states. And each of those states have 4 different Q values. So this is a much more difficult problem for Steve to solve. And it actually turns out to be almost impossible for it to happen using this implementation, because it will just take a very long time for it to go through each possible state. And that is actually left as an exercise for you to explore this concept of function approximation, which allows Steve to approximate the value of different states by seeing what the value of the other states near those states are, and that will allow it to solve the problem a lot more quickly. So that's reinforcement learning in OpenNERO. I hope you enjoyed it.